Welcome back, Year 11s. We're going to now look at electrical potential and potential difference. And there is technically a difference between the two of them, even though they're measured in the same units. So, first of all, EMF. EMF stands for electromotive force. This is what I was talking about earlier when I say it's a force, but it's not actually a force. We don't measure it in newtons. It is actually the energy given to charges. It's not a force acting on them. The name has been retained for historical reasons. There you go, Jack. Don't need to argue with us now. It is the energy per unit charge which has been made available by the generating mechanism, such as a battery or a generator. So EMF can otherwise be stated as the external work. Remember, external work is the energy applied from an external object, expended per unit of charge to produce an electric potential. So the SI unit is the volt, which is 1 joule per coulomb. This is quite often referred to just as voltage. As it is the electric potential per unit charge, it is often referred to as electric potential or just potential. So potential difference. So when a battery is connected to a circuit, it creates an electrical potential. Components in a circuit use some of this potential energy. The potential difference is defined as the difference in the potential energy of the charges as they are used by the conducting material. This is easily described using a diagram. Here's my symbol for a battery, and here are two light globes. And we go back. So let's just say we have got a 9-volt battery. That 9 volts is the electrical potential for the circuit. Now these two light globes each are going to split this electrical potential. So this will have 4.5 volts go through it, and this will have 4.5 volts. So that 4.5 volts means the voltage that goes through it is going to be slightly, it's going to be measured as 9 volts going in, 4.5 going out here, and here will be 4.5 going in and 0 left. So this is referred to as the potential difference, because there's a difference in voltage that enters and leaves the component, because the component uses some of that electrical potential and turn into other forms. Now, in this case, a light globe turn into heat and light. And if it's really dodgy, sound. If your light globe's creating sound, go bin it. Potential difference has units of volts, and it's quite often rearranged as, so voltage is amount of energy per charge, so it's quite often rearranged as energy flowing through the circuit is equal to amount of charge flowing through the circuit times by the voltage. So here, your battery, once again, this is your electrical potential, and your lamp would be your difference in voltage or your potential difference. So quite often they'll write this as W over Q. So W is work. Work is also referred to as the change in energy. So the voltage is the amount of energy used up in the circuit divided by the charge that's being moved through the circuit. So question for you. When an electric cell is connected to a circuit, electrons flow away from the negative terminal in the circuit. Within the cell, they flow to the negative terminal. So why would this occur? Electrons, these guys are negatively charged. So in the wire, they get these negative charges get attracted to the positive charge of the battery. But in the battery itself, the electrons actually have to then go from the positive side all the way through to the negative side to keep the circuit going. So why would it want to do that? It's because there's a chemical reaction that does the work on the electrons to take them from the low potential energy to the highest potential energy, or the negative terminal. So the chemical reaction is what's creating the energy to get it out of the battery. If you don't have a chemical reaction, your battery's flat, which means it's not pushing electrons to the negative terminal to keep the circuit going. That's why your electrical device does not work when you've got a flat battery. Question 6. What energy is required to move 20 coulombs of charge across a voltage of 3 volts? Well, E is equal to QV. So Q is 20 and V is 3, so V 60 joules. There you go. Alright, an extension question. This is a good exam type question. Electrons in the TV tube are accelerated from a potential difference of 2 kilovolts. Given the mass of an electron is 9.11 times 10 to the minus 31 kilos and their charge is 1.6 times 10 to the minus 19 coulombs, determine the work done on the electrons. Well, work is the same as energy, which is equal to QV. So, to find out the amount of work done, we go 1.6 times 10 to the minus 19 times by 2 kilovolts. Kilo is 1,000, so it's 2,000. And we throw that into our calculator. 3 times 10 to the power of minus 16 joules. Now, how much kinetic energy is done on the electrons? Well, if we look at it, work is equal to energy. The energy is performed on this electron is just to accelerate it, to move it. So moving is kinetic energy. So that is also 3 times 10 to the minus 16. And then the final velocity of the electrons, assume they were initially at rest. Well, E for kinetic energy is equal to half times mass times by velocity squared. Substitute it in. 3 times 10 to the minus 16 is equal to half times by mass, which we actually know. 9.11 times 10 to the minus 31 times by V squared. So V squared is equal to 6.59 times 10 to the power of times 10 to the 14 meters per second. V is equal to 2.57 times 10 to the power of 7 meters a second. Now, that is nearly 10% the speed of light. Now, Jack is probably also fuming because we have not taken into account relativity, which relativistic effects would actually mean the electron is going slower. But Jack, we are year 11 physics, not year 12. We don't need to take into account relativistic effects just yet. So we assume that the electron has accelerated its way all up to 2.57 times 10 to the power of 7 meters per second. The full working can be found on the next slide. Okay, year 11s, thanks for listening, and I'll see you tomorrow.